let's start with the understanding the term multi-phase microfluidics. So, this course, the title of this course has two terms, multi-phase and microfluidics, and first we will try to understand what does the term multi-phase mean and what does the term microfluidics mean, and then try to understand each term individually and then look at the different aspects of the course. So, the term multi-phase has two syllables into it, multi and phase. Multi means many and phase generally refers, in a general sense, it refers to the thermodynamic state of the matter, which is generally gas, liquid and solid. So, in a general sense, multi-phase refers to flow of gas liquid, gas solid, liquid solid or gas liquid solid. And however, it can so happen that two immiscible phases can coexist or multiple phases can coexist in the same state of matter. As in this course, we are concerned with the fluids or the flow of fluids. So, such a case can arise when we have flow of two immiscible liquids. For example, water and hexadecane flowing in a channel and the interaction between them in terms of the flow pattern, flow structure, flow behavior, the size of the droplets or the different flow structures, for example, parallel flow, annular flow and so on and so forth. So, that is about what the term multi-phase means. Now, coming to microfluidics. So, microfluidics, as the term suggests, micro and fluidics. So, micro is the flow at micro scale. It can be flow in a channel of micron size or flow in a constriction of micro size. Sometimes it can also refer to the flow of micron sized droplets or bubbles or particles. So, it is at the micro scale. When I say micro, it can be from few microns to few hundred or sometimes few hundred microns, or sometimes it can be even few millimeters. And fluidics is flow or manipulation of fluids. So, basically what we are going to study in this course, multi-phase microfluidics, is what happens when we have flow of more than one phase in microchannels. Okay. So, in last 2 decades, there has been lot of emphasis in microfluidics and nanofluidics, or in general, if I talk about microtechnology and nanotechnology. If you look at the trend in the technology has generally been towards miniaturization, looking at the small and small. So, if we look at what Feynman envisaged in his now very popular or very celebrated lecture titled as "There is Plenty of Room at the Bottom," where he looked at the possibility of manipulating matter on an atomic scale. That might be probably the smallest scale possible that can be manipulated, and he described interesting ramifications of such phenomena. So, I would suggest you to look at the lecture and understand the ramifications that he described about 60 or about 60 years ago without any real development in the field of microtechnology and nanotechnology. Okay. So, in microfluidics, what we are looking at is flow at small scales. So, now the question comes that how small is small, at what size can the channel be considered in microchannel? You will see that in the literature, the flow happening from few microns or say tens of microns up to few millimeters, the term micro has been used frequently. So, the question arises, what is micro scale? So, in my opinion, the first question we should ask, what is so different about microfluidics or flow in microchannels that we need to study it separately? What are the effects or what is the physics that was not present in small diameter channel or in conventional channels, but has become dominant in the micron size channel or small diameter channels? When we look at that effect, then probably it will be easier for us to define a cutoff, if there is one such thing, for classifying the channel to be a macro channel or channel to be a micro channel. So, let us look at some of these size effects. So, if we look at the different size effects can be classified into these three different classifications. And when I look at or when I talk about the classifications, I would suggest that not only microfluidic, but nanofluidic or going to a small scale, one need to consider, one need to take into account, one need to check, are these effects changing, are these becoming important, or are these losing the significance. So, let us look at these effects: non-continuum effect, surface dominated effect, low Reynolds number, or low diffusion length effects one by one. So, let us look at continuum hypothesis. Many of you might not be aware of what the continuum hypothesis is. So, let us look at. We all know that a fluid or a matter, a gas, a liquid, a solid, they are all constituted of small molecules, and these molecules are randomly in motion depending on what state of matter, the distance or the mean free path will depend on that. So, basically they have in a room or in the space, there are number of such molecules, millions or trillions of those. Now, when we looked at the description for the engineering purposes, for example, for the fluid flow, we describe the properties of such systems or properties of such materials, these fluids, liquids and gases, as a continuum. That means we do not consider that at one particular point of space there is a molecule or there is not a molecule. We take as has been written here, that the molecular effects are lumped together to space average macroscopic or continuum based quantities such as density, temperature and velocity. We can do so because the number density of molecules is so large that we can treat the molecules to be continuum and analyze the fluid or analyze the system. So, for reference, a volume which have 10,000 molecules, there is 1% statistical fluctuation in these average quantities. So, probably that should be good enough. So, how we describe, because then the question will come that when you go to smaller and smaller scale, probably you might not have enough molecules to assume it to be continuum. So, every time we go to a smaller scale, we need to check the continuum hypothesis. So for air at standard conditions, this volume is about 3.7 into 10 to the power minus 22 meter cube, in which one can expect to have about 10,000 molecules. Okay. So if we look at the continuum hypothesis, it is often described or determined by a non-dimensional number, or it can be described by a non-dimensional number which is known as Knudsen number, and this Knudsen number is the ratio of two length scale. One is the length scale for the molecular motion, which is mean free path of the molecules, and another one is the character length scale of the problem or of the system or of the channel that we are looking at. So when it is obvious that when the mean free path is very small or sufficiently small, then the characteristic length scale of the problem, then we can assume then we can use the continuum hypothesis, then the continuum hypothesis will be valid. So for a low value of Knudsen number, where that means the low value of Knudsen number means the mean free path is very small, then the characteristic length scale of the problem, the continuum hypothesis is valid. So for those who do not remember what mean free path is, the mean free path is the distance traveled by the molecules between collisions. So the molecules of a fluid, they are moving continuously in the fluid, they have thermal fluctuations, and because of that they will collide with each other very frequently. So the distance that the molecules in an average sense travel between the two collisions, that is called mean free path. And for air and other gases, this value is as you would expect, that this will be the largest out of the three phases. It will be largest for the gaseous phase. So that is about the order of 10 to the power 8 meters for air and other gases. So it can be considered, the literature suggests that when the Knudsen number is less than 10 to the power minus 2, then fluid can be considered continuum, and when it is greater than 1, then we have to consider it as free molecular flow, and in between there are two different classifications, slip flow and transition flow. Based on these, we can see that in a channel, the characteristic length scale will be few micron, say let us say 10 micron. So in such a case, the Knudsen number will be above 10 to the power minus 2. So the continuum hypothesis will often be valid in microfluidics. Having said that, another effect of continuum hypothesis is slip boundary condition at the solid surfaces, and it has often been a contentious issue, that is there a no slip condition at the microchannels, or is there a slip condition at the in microchannels. So let us look at what does this no slip and slip business is about. As we all know, if you have done a course, an undergraduate course in fluid mechanics, and you have studied about the viscous fluid flow, then you will know that at a surface, the no slip conditions refers that on a surface, the velocity of the fluid will be equal to the velocity of the surface. So that means there is no slip between the solid surface and the liquid layer adjacent to it. This is purely based on the from the experimental observations. So, some experiments in microchannels have suggested that there is some amount of slip at the walls. However, another group of researchers, another school of thought is that the slip behavior that has been observed in microchannels is because of the roughness effects or the air trapped in the channel, and not because that there is the no slip condition is not valid. So, I would suggest you to be aware about the fact that in microchannel there can be a no slip condition, and you, while analyzing data, you should look at these effects. We will talk about this a bit in detail in later lectures. I would also like to point out here that when there is slip condition, it can often be modeled using Navier slip condition, which suggests that if this is your wall and the liquid flowing adjacent to it say from bottom to top, then in case of slip there is some non-negligible velocity at the wall, and if you consider a linear variation of velocity inside the wall, then the length at which the velocity will be 0 is known as Navier slip condition. So, the parameter for such a model for the slip will be the slip length, which is lambda slip, and this has to be either found out from experiment or some other means. Okay. So, the next size effects we are going to discuss is about surface dominance. So, in microchannels, surface area to volume ratio. So, let us write this surface area as A and volume as V. Surface area is proportional to length squared and volume is proportional to L cube. So, we will have this as 1 over L. The ratio of surface area to volume varies with respect inversely proportional to the length. So, for 1 meter channel, this value will be about 1. For 1 mm, it will be about 10 to the power 3, and for 10 micron, this value is going to be 10 to the power 5. And that is what makes surface effects so important in microchannels. If we look at number of physical effects, some of them are proportional to the volume and some of them are proportional to the surface area. So, in general, this ratio in a conventional channel or in a macro system, A by V is small. So, the surface effects may not be so dominant in large channels, but as we can see, as the size decreases, this ratio becomes important, or this ratio becomes larger and larger. So, surface forces become important in large diameter channels. Now, we need to look at a bit in detail what these surface effects can be. So, as I have listed here, these can be friction in liquids, this can be viscous effects, it can be electrostatic effects. So, and the same for the same region, you might hear that in micro channels the heat and mass transfer rates are very high. So, if you write the heat transfer rate for convective heat transfer, you will write Q is equal to H A delta T, where A is the area of the surface. So, this area of the surface or the Q is proportional to the area of the surface. Similarly, in the mass transfer, the rate of mass transfer is proportional to the area of the surface. So, higher the area per unit volume, which is interface or which is area density, higher this area, higher the rates of heat and mass transfer going to be. So, that is the reason that in micro channels there are number of heat transfer applications of micro channels, for example, in electronics cooling. In two-phase flows or in multi-phase flows, say for example, gas liquid flow, the interfacial area that one can achieve in micro channel is 2 or 3 order of magnitude larger than one can achieve in smaller channels in general. So, the interfacial area density is the interfacial area, we represent this by AI per unit volume, is again proportional to 1 over L, and whereas the interfacial area will be order of 10 or 100, in conventional channels it can go up to 10 to the power 3 or more in micro channels. So, it will be beneficial or it will be advantageous to conduct fast gas liquid reactions, for example, which are limited by the rate of mass transfer. So, if one have high interfacial area density, that means if one have high interfacial area available for the mass transfer, then the rate of mass transfer will be high and the yield of the fast reactions can be better in microchannels. Similarly, in the electronics cooling or where one need to remove high heat fluxes, any such applications, one can remove very high heat fluxes by the use of microchannels. Okay. Now, coming at the third effect, which is you can say another surface effect, that in microchannels the viscous forces are dominant. So, viscous force they can be represented by a Reynolds number, which is the ratio of inertial forces and viscous forces, or in terms of this the stresses. So, Reynolds number is generally defined as rho d u over mu, where u is the velocity of the fluid, and we will also try to see here how we can represent this in terms of the two stresses. So, mu u over d, which is the length scale of the problem, and inertial stress is generally represented as rho u square. So, the ratio of rho u square and mu u by d is the Reynolds number, and at low length scale the d is low. So, in microchannels the d is low, the velocity will also often be low. So, we will have low Reynolds number. That in turn mean that viscous effects are dominant. So, viscous effects are dominant, and the other thing is that the transverse length scales are small. So, when the viscous effects are dominant, that means the flow is laminar. Now, in general, in conventional channel, flow is often turbulent. So, the turbulent fluid means that there will be a number of eddies, and the mixing of the fluid occurs because of the turbulent flow. So, in a number of applications, especially in chemical engineering, one need to have the mixing of the fluid. So, whereas one can achieve the mixing by the turbulent nature of the flow, it becomes a problem in microchannels. So, if you look at the literature in microfluidics in last 2 decades, there have been a number of efforts to devise different strategies to achieve mixing in microchannels, because this is not, the flow is not turbulent there, and one need to devise new ways of mixing. This can be by the means of electrokinetic effects, utilizing the electrokinetic effects, or utilizing a Mandiering channel, or many other passive or active scales or active means of mixing. So, this can be a disadvantage, but at the same time, when one have the flow as laminar, then one can predict it very accurately, one can control it in a better manner, one can know what is going to happen, and knowing that, one can try to manipulate and control the flow and do number of things precisely the way one wants to do. So, that is the advantage of having low Reynolds number, but at the same time it is also has a disadvantage that no inherent mixing is present in the flow. The small length scales or the transverse length scales are small. So, that means the velocity gradient in a channel. So, if you look at diffusion that is happening, the length scale over which the diffusion is required is smaller and smaller. So, any diffusion process, it might be momentum transfer, which is viscous, where the diffusivity is or momentum diffusivity is kinematic viscosity, and it can be heat diffusion or it can be mass diffusion. In all cases, the diffusion lengths are small. So, the gradients, velocity gradient or the temperature gradients or the concentration gradient will be large, and the rate of this transfer will be larger. In the fluid flow, because the viscous force is dominating, so the pressure drop per unit length or will be larger. Okay, and we have already discussed that mixing is an issue because the flow does not become unstable and turbulent. So, viscous damping dominates the flow in most of the cases. Okay. So, one of the effects surface tension, one of the surface effects that we have looked at in microchannels is that what can the viscous effects do. Now, another physical phenomena which becomes very important in microchannels is surface tension. So, what is surface tension? Surface tension, of course, occurs at an interface. So, an interface is a boundary between two fluids. So, for surface tension to occur or surface tension requires that there is an interface. So, it is an multi-phase phenomena. If there is an interface, then it will have multi-phase associated with it. Now, what is surface tension? So, if we have a bulk fluid, let us talk about having a liquid and a gas above it. If there is a fluid molecule in the center, it will be attracted by different molecules from all the sides. So, it will have an equilibrium. Whereas, a molecule which is at the surface, it will be interacting with the molecules in the bottom half, with the liquid molecules, whereas the interactions with the gaseous molecules will be relatively weaker. So, there will be a net tendency, or there will be a net pull on the molecules towards the inside, and that tension, and that will be that is what in a microscopic sense or in a macroscopic sense is referred to as surface tension, and because of this effects the fluid tends to minimize its surface area, so that the surface energy can be minimized. And again, this is a surface phenomena, and it happens only at the interface between the two fluids. So, as we have discussed previously, that when the surface area to volume ratio becomes higher, surface tension becomes important. So, there are number of applications in microfluidics where the surface tension effect is taken into account, or it is being explored, or it is utilized to manipulate the droplets or liquid bubbles and so on. So, there is a non-dimensional number which is called bond number, which compares the buoyancy force and surface tension force, and this is represented by sigma over d, and buoyancy force is delta rho g into d, so rho g h, yeah. So, that will be delta rho g d square over sigma. So, this number is also known as Atwas number, and this is often used in gas liquid flow to demarcate a boundary between the mini channel or between the micro channel and the large channels. So, this can be used to find out for a particular gas liquid system at what size one will have the surface tension effect dominating the gravity force. So, for example, in large channels one often observe stratified flow, where the liquid is at the bottom, the gravity is acting in this direction, and the gas is at the top, and one call it stratified flow. However, in large diameter channels, one observes stratified flow. However, in small diameter channels, because of surface tension, the interface does not remain like this. One has annular flow and bubbles forming. Either one will have bubbles forming there, or one can have annular flow where liquid is in between and the gas is around it. So, the bond number is, as you can see, proportional to d square. So, when the length size becomes smaller, the effect of gravity becomes smaller, which is a body force, and the surface tension start dominating the flow, and you will see number of effects on that. So, another non-dimensional number which compares surface tension with another force which is important in microchannels, which if you can remember we have discussed just now, is the viscous force and surface tension. We often define the ratio of these non-dimensional numbers in terms of forces, but in my opinion it is better to define this in terms of stresses, because that is what we generally write while deriving these. So, for example, viscous stress is given by mu u by d, and surface stress or surface tension generated stress is sigma over d. So, this will be mu u over sigma. Okay. Another non-dimensional number which is called Weber number, and it is a ratio of inertial force and surface tension force, or the stress is because of the two. So, the inertial stress is given by rho u square, and the surface stress, surface tension generated stress, sigma over d. So, this is rho u square d over sigma. Okay, so that is Weber number, and one can see that Weber number can be defined as a product of Reynolds number and capillary number. Reynolds number is inertial effects divided by viscous effects, and capillary number is the ratio of viscous effects and surface tension effects. So, this becomes the ratio of inertial and surface tension effects. So, by the way, when we talk about liquid, there also we have similar effects present, but this will not be so dominant as in gas liquid, and this is often known as interfacial tension in the case of liquid. In case of miscible liquids, the interfacial stress is 0. For example, between a salt water solution and a fresh water solution, the interfacial stress is 0. Another effect that has been explored or utilized very well for several microfluidic applications, another surface effect is called electrokinetic effects. So, how does this come by? When we have a charged surface, or not charged surface, when we have a solid surface and it is brought into contact with a aqueous medium which is polar, which has ions present in the liquid, then there is a charge that is established on the surface. This charge can be positive or negative depending on the conditions, depending on the aqueous solution, what is there in the aqueous solution, depending on what the surface is. So, the surface acquires a charge, and now the aqueous solution has ions which are present in it, in the aqueous solution, and the surface has the charge. So, as a result, the ions will have thermal motion, as well as the ions near the surface will have a electrostatic force because of the attraction or repulsion from the surface, or from the charge present at the surface. So, a equilibrium will be established, and a certain charge distribution or a certain distribution of the ions will happen just adjacent to the surface, and this charge distribution is known as electrical double layer. So, this electrical double layer does not have significant effect in large channels, because it can, any such effect can be neglected. However, this can be utilized for number of applications in electric in microchannels. So, the two effects which are often used in microchannels are electroosmosis and electrophoresis. So, electroosmosis is that the stationary charge surface, which is not necessarily it is because of the electric double layer. In general, if the surface is charged and when a electric field is applied, the movement of liquid. So, when an electric field is applied on a stationary charge surface and the liquid move, then it is known as electroosmosis. On the other hand, electrophoresis is that a charged surface itself moves relative to a stationary fluid because of an externally applied field. So, you can see the difference between the two effects. Electroosmosis is that when an electric field is applied, the liquid moves over a charged surface. It is called electroosmosis. But when the solid or the charged surface itself moves relative to a stationary fluid, it is called electrophoresis. Now, two other effects which happens because of these electrokinetics, two different potentials are induced. One is called streaming potential and another one is called sedimentation potential. So, electric potential which is induced when a ion containing liquid, when a liquid which has ion and it moves over a surface which is charged, then the electric field or the electric potential that is generated because of this is called streaming potential. So, because of the stream of the fluid which contains ions, when it moves over a charged surface, the potential generated or potential induced because of this motion is called streaming potential. On the other hand, sedimental potential is the potential that is induced when a charged particle moves related to a stationary liquid. So, for example, a charged particle when it sediments or when it drops from top to bottom, say because of buoyancy, then it will induce a potential when it is moving in a stationary liquid, then this potential is known as sedimentation potential. So, in summary, in this lecture what we have looked at, what are the size effects which are important in microchannels. Initially we looked at three phenomena, or we discussed three phenomena which might be important. One is the continuum hypothesis. We looked at what continuum is and is it valid in microchannels, and it appears that most of the cases that we consider in microfluidics, the continuum hypothesis is going to be valid, but it is a good practice, or one need to look at the validity, especially the no slip or slip boundary condition. Then comes the surface effects. We looked at that because of the high surface area to volume ratio at a small scale, the surface effects becomes dominant, which causes high rates of heat and mass transfer. The diffusion paths are small, so again which causes the high transport rates. We looked at three specific surface phenomena: viscous effects, which gives rise to low Reynolds number and the flow is laminar. Then the surface tension effects, which have number of interesting applications, and the third one is electrokinetic effect. So we will explore more and more the surface tension effects in this course. So we will look at gas liquid flow more, and we will look at both diabatic as well as adiabatic flow in microchannels. We will look at droplet microfluidics, bubble generation techniques, etc. in the microchannels. Thank you.